Okay, we're ready to look at the third segment of our lectures on Chapter 8, dealing with the Jovian moons, the rings, and Pluto. In particular, let's look at the Jovian moons. If we look at Jupiter, Saturn, Uranus, and Neptune, we find that all four Jovian planets have rings. And all four rings lie around each planet's equator. So they all have this in common, as well as the ring particles obey Kepler's laws, which means that there's a relationship between the time period squared to the distance of the particles cubed from the planet. So they obey, and they follow in the elliptical orbit, so they obey Kepler's laws. And the appearance of the rings are connected to the small moons of the planets themselves. So we'll see variations, kinks and stuff to the way that the ring particles move. And this is in relation to the location of moons within the ring system. Also the gaps as well. So they obey Kepler's laws. They're around the planet's equator, and as we'll see later, we can add one more thing, is that the rings are all found within the planet's so-called Roche limit. Four rings lie within the planet's Roche limit. The Roche limit is the distance at which a planet's tidal force will break up a satellite. For instance, here's a planet over here. Here's the Roche limit. Here's a satellite. As the satellite moves in, maybe over time, and gets closer into the planet, it will then receive more of a differential gravity force. In other words, parts of the planet will be pulling it on one side, part on the other side, and so instead of just having a full gravitational force on the object, it will be pulling in relation to the size of the object, and that will cause a flex on the object itself. And if the satellite were to fall within too close of a range, which is what we call the Roche limit, then it will disintegrate into smaller particles. And that's what we would see in the ring system then. For a satellite that has the density that is similar to the planet's density, the Roche limit is 2.5 times the radius of the planet, or 2.5 times the radius of the planet. So in the case of Saturn and Jupiter, which has density on the order of 1, if the satellite itself were on the order of a density of 1, then at 2.5 times the radius of the planet, you would expect it to disintegrate into ring-like material. Most of the satellites probably would be about twice the density of those planets, but pretty much follows the same order of relationship. Let's look at Saturn's rings. This is an enhanced photo, color enhanced photo of Saturn's rings. Saturn's dimensions, rings dimensions, is 200,000 kilometers in diameter, which would be about 120,000 miles in diameter, but only a few hundred meters thick. So the ring system itself is relatively thin in relation to the diameter of the ring system. Here's a backlit picture of Saturn and the ring system. This is a recent picture, and it's pretty neat, I think. But it clearly shows the features of the Saturnian ring system. Ring system was first recognized as such by Christian Huygens in 1659. Now we note that Galileo had seen the rings of Saturn way back in 1609, but he called them the ears of Saturn. He didn't know what they were, and with his resolution, they just looked like ears on the planet. But Huygens recognized that they were indeed rings. The rings are probably 1 billion years old, so the fact that they were first recognized more than 300 years ago is great, but they've been around a lot longer than what we've recognized. And the rings lie in Saturn's equatorial plane. Here's a nice recent picture taken by Cassini showing some detail to the rings and showing that they seem to be consisting of snowball ice particles all conglomerated together to form the rings. Saturn's tilt changes over the course of time in relation to our perspective, and if it actually happens to have a tilt with respect to us, then that makes Saturn's rings visible and makes Saturn brighter as well. And we can see in these two views, in view A, Saturn's ring system is edge on, so it's very hard to see the rings. And in view B, it's we have more of a tilt, so we can begin to see the ring system. Here's a composite view of a look at Saturn over the years of 1996 to 2000 using the Hubble Space Telescope. And we see that as we approach 2000, Saturn had more of a tilt in relation to us. And you can see that not only the planet but the ring systems makes the whole system look brighter. In fact, at solstice, which would be when the Saturn is at its greatest tilt with respect to us, the ring will double Saturn's brightness. Here's a look at Saturn over recent years in the years 2000, from 2002 up to 2009, and we see in the year 2009 Saturn's ring system is edge on to us, and hence would basically make the ring system disappear for that 1 year of 2009. So that would be what we might call the Saturn's equinox with respect to us. And then from that point, over the next few years, next 8 years or so, Saturn will again approach solstice in the year 2017, at which point it will be at its brightest, and we'll be able to see the ring system at its best possible clarity. Here's Saturn's basic ring system, 3 main rings. And starting from the outer part of this, we have the A ring, which has a particular gap in the center of it. We have the B ring and the C ring, all comprising Saturn's main rings. This large gap between the A ring and the B ring is called the Cassini division, named after Cassini. And this little gap in the A ring is called the Encke division, named after Encke. This is a color-enhanced ultraviolet photograph of Saturn's ring system. That's the A ring. And here's the C and B ring, ultraviolet. So that means colors were assigned for each ultraviolet frequency to give you this mapping. Here's the Encke gap within the A ring, and we can see a real small ringlet through the gap, and it's twisted and knotted because there might be some smaller rocks or smaller moons that are basically affecting this ringlet of material in the center of this gap. Here's a Wavemaker moon in the Keeler Gap of the Saturn ring system, and we can see that the presence of the moon causes a gravitational wave on the particles in the above and below in this picture in the ring system. So the moons are affecting the appearance of the ring system. And here's a neat picture of Saturn's ring system taken recently in 2009. We have Titan, and it's backlit, so you can see its atmosphere in the light colored here. And then we have Enceladus kind of infringing on that image and in the foreground, and we have the Saturn's ring system right here. So it's just a beautiful picture taken by Cassini. What about the formation of Saturn's rings? Two theories for the formation of the ring system. Possibly it is due to the destruction of an icy moon that fell within the Roche limit of Saturn. In other words, kind of spiraled in and at some point fell within that limit, disintegrated into a bunch of particles and formed the ring system. Or maybe it was icy matter that formed with Saturn at the same time, but also formed too close to Saturn within the Roche limit, so it never had a chance to coalesce into a moon, and hence it just remained particle matter, icy particle matter, and hence formed the ring. Now we talked about this Roche limit, where an icy moon might fall within this limit, disintegrate into a ring-like pattern. Space probes and small satellites are not necessarily subjected to the Roche limit because gravity is not the dominant binding force of these objects. For a moon, gravity is, and a moon is consisting of material that's been pulled together by gravity, and hence gravity can affect it more. Whereas in the satellite, if you had a metal satellite, you have other forces at work, bonding forces within the metal and so forth, that make it a little bit more robust against just plain gravity pulling it apart. And also, the smaller you get, the surface to volume ratio gets larger. Hence, the Roche limit is less effective on the smaller particles. Hence, we saw that these smaller moons exist within the ring system, and they're not being disintegrated because they have a surface to volume ratio that's greater. And it's only the large objects that get to be disintegrated in that way. Here's some observations taken by the Voyager spacecraft that first observed many of the features of Saturn's rings. The rings are actually composed of thousands of ringlets with changing structures themselves. Nearby moons create ripple waves in the rings, which we saw in earlier photographs. And there are 20 narrow gaps scooped out by tiny moonlets, creating these gaps. Also, Voyager observed that there are spokes within the ring system, and these kind of darkened areas of lines that pass across the ring system, and this might be driven by the magnetic field of Saturn. Is at least one hypothesis that it might be a magnetic effect or a gravity effect on the ring system. Here's another look at these darkened spokes on Saturn's ring system. And here's a recent picture of the spoke effect, 2009, and we can see some discoloration here and a radial pattern across the rings. It is said that since Saturn, when Voyager went by Saturn, Saturn was near a equinox position with respect to us. In other words, rings edge on to us, and the spoke pattern was more clearly seen at that time. Since then, it's been harder to see the spoke pattern, but now in 2009, Saturn is edge on again, and we see clearly the spoke pattern. So there seems to be some kind of relationship to the perspective of Saturn and the appearance and visual appearance of these spokes. The Cassini division, which is the largest gap in the Saturn ring system, is caused by the presence of the moon Mimas, which is resting in that division. There's a faint D ring inside the C ring, and the E ring, which is to the outside, is caused by Enceladus. Enceladus has those ice volcanoes that we talked about earlier, spewing out snow. Some of the snow falls back onto the moon. A lot of that snow stays out into space and is what is producing the E ring that goes around Saturn. So E is for Enceladus. Here's the F ring. And the F ring is being shepherded in by two shepherd moons on opposite sides of the ring. The gravity of those moons is helping to hold that ring system into place. So there are moonlets that help shepherd the rings into place. And they also cause the ringlets to braid and kink according to the gravity of the moons. Well, we said that all the Jovian planets have rings, and in fact they do. And Jupiter has a ring. It's not as spectacular as Saturn. In fact, it's very hard to see from Earth, but it was discovered by Voyager in 1979. So it was the first ring system discovered by a separate spacecraft. It lies in Jupiter's equatorial plane. Here's an artist's conception. And here's the enhanced picture of Voyager's picture of Jupiter's faint ring. It's difficult to observe from Earth because the ring is not necessarily composed of icy particles that reflect well, but instead of rock and dust. It's discolored by the incredible radiation being transmitted by Jupiter, and it's edge on to us. Jupiter is straight up and down. The ring system is around its equator, so to us the ring system is always edge on, and hence, as we saw with Saturn recently, when the ring system is edge on, it's very difficult to see from Earth. Here's another look, recent look at Jupiter's ring system. It's actually 4 ring systems, 2 gossamer rings. Gossamer meaning it's kind of real thin type, veil type material. And it has a main ring and a halo ring. So really 4 rings making up Jupiter's very faint ring system. Uranus has a ring system. And this was discovered in 1977 from Earth when Uranus passed in front of a star, and the ring system caused a occultation with the star, so the light of the star was being blocked by the ring system of Uranus, and hence you could see the ring system of Uranus. In 1986, when Voyager 2 flew by Uranus, the rings were at solstice, so that we could actually see, since the pole of Uranus was pointing towards the sun and pointing towards us, we could see the full effect of the rings of Uranus at that time. But in 2007, the rings were edge on, and hence they visually would disappear from Earth. And now we're proceeding on our way back towards 2028, when the ring system would be in full view from Earth again. Here's a progression in recent years from 2001 to 2007, at which point the rings of Uranus came edge on and were most difficult to see in the year 2007. There are, as to current count, 13 separate rings in the Uranus ring system. They are all dark, narrow, and widely spaced, as we see in this photograph of these rings. The last two were discovered by Hubble in 2006. Here we have a picture of Uranus with the main ring systems, and then Hubble discovered these two most outer rings here. If we enhance this with a diagram here, see Hubble discovered these two new outer rings, giving Uranus at least 13 ring systems. At the same time, Hubble also discovered a couple more moons as well. And Uranus's rings, at least some of them for sure, are shepherded in by shepherd moons, just like what we saw at Saturn. So the moons on either side, the gravity of those moons help to ensure that the rings stay on their path. Neptune has rings. All of the Jovian planets have rings. Neptune has 4 main rings. We have 3 of them here, which are relatively thin, 1, 2, and 3. And then there's a 4th one, which is a broad gossamer type ring. And we can see it here, at least the edge of it indicated by the red here. And that's just this broad colored ring that kind of superimposes over a couple of the other rings. The outermost ring contains clumps of matter, probably caused by shepherd satellites. And as with Jupiter's ring, this ring system of Neptune was discovered by Voyager. So Voyager discovered 2 of the ring systems, Jupiter and Neptune, and the other 2 ring systems, of course, were discovered by someone on Earth. Saturn's ring systems and Uranus ring system discovered on Earth. So 2 by Earth, 2 by Voyager. The playing field is even. Pluto. Pluto was named after a Disney character who looks like the planet. If you look at this Hubble Space Telescope and you see this darkened area over here, you might imagine that there was a mouth there. And then you see this area over here. This gets a little bit lighter with dark here. It looks like a nose. And then this light area here looks like an eye. And in fact, by resemblance, it looks just like Pluto, the Disney character. No, that's not right. That's not why Pluto was named Pluto. Pluto was named after the Roman god of the underworld who reigns over eternal darkness. And that's a good choice because Pluto is way out there, far from the sun, doesn't get much light, so it's out there. It's reigning over eternal darkness because it's far from the sun. So that's a better name for Pluto. Here's a Hubble Space Telescope 3-dimensional mosaic of Pluto, kind of extended outward, and we can see that there are indentations and lighter areas. This indicates at the top you see it bright, and at the bottom bright as well, so there's bright polar ice caps and possible crater topography like our moon, but it's really hard to garner much more than that from this picture, just light and dark. Pluto was discovered by Clyde Tombaugh. Its position was predicted based on irregularities of Uranus's orbit by astronomer Percival Lowell. Percival Lowell was the premier astronomer of his day, and his apprentice was Clyde Tombaugh. And in 1930, Tombaugh discovered Pluto in much the same area where Lowell predicted it should be. So that was a good thing, but it was found later that Pluto's mass was far too small to create those observed irregularities in Uranus's orbit. So really, Pluto was discovered purely by pure luck. So the first two letters of Pluto are the same two initials of Percival Lowell, and probably was part of the reason why Pluto got its name, because it was discovered where Percival Lowell said it should be. However, you could just as well say that Pluto was named after pure luck, because it was discovered by pure luck that Tombaugh looked in that area and discovered this world. If we were to compare Pluto to our world, we would see that it would take 5 Plutos to extend across our diameter of the Earth. So Pluto's is much smaller than the Earth, and its radius is only 20% that of the Earth. Recently, Pluto was demoted as a planet in 2006. So we're going to look at the argument of why maybe it should be a planet and why maybe it shouldn't be a planet. Here are some reasons to classify it as a planet. Reason number 1, grandfather clause. We've been calling it a planet for years, so why not? This was probably a good reason up to 2006, because Pluto was discovered in 1930, and up to 2006, that's 76 years of calling it a planet, and people grew up knowing and thinking of Pluto as a planet. So you have 76 years of that. Why not just keep it going? Near perihelion, the closest approach of Pluto to the Sun, Pluto actually comes closer to the Sun than Neptune, and at that point it warms up enough to develop an atmosphere. So it actually has a little bit of outgassing and develops an atmosphere like a planet would have. It sometimes moves closer to the Sun than Neptune, so it's going around the Sun, and it's closer than a known planet Neptune sometimes. So maybe that should give it planetary status. Pluto has a moon, Charon, which we'll talk about in a moment. In fact, Pluto has 3 moons now. Recently, Hubble did a high-resolution picture of Pluto, and it's discovered 2 more moons of Pluto. And the best reason to classify Pluto as a planet is that it was discovered by an American, and we don't want to give that up. It was discovered by Clyde Tombaugh, an American, so it's difficult to not take that credit. Well, here are some reasons to not classify Pluto as a planet. It's neither terrestrial nor Jovian. Its density is too large for a Jovian planet, too small for a terrestrial planet. It doesn't fit in with any of the 2 major categories of planets that we know of. Its size, mass, and density are more similar to the large moons of the Jovian planets, especially Triton. So it's more moon-like. And we now know several Kuiper belt objects that are similar to it, discovered in the 1990s and the 2000 era. So there are a lot of icy objects similar to it. So there's a problem there. If we keep Pluto as a planet, we're going to have to start naming these KBOs planets as well. And some of them we only see for a couple of years, and then they're gone for thousands of years. So we're going to have these planets that we never see for thousands of years, and we're going to start calling them planets. And that would be a major problem. Pluto is not in the ecliptic plane, so it does not obey orbits like the other planets do. And here's the kicker. In 2006, a planet was defined as something that clears away its neighborhood so that there aren't other planets nearby. Pluto does not clear away its neighborhood. It's got these other objects nearby it, these other Kuiper belt objects nearby. So it doesn't clear away its neighborhood. It's not a planet with that definition. And like we said, if it were a planet, then we'd have to start naming these other objects that go around the sun as planets. In particular, Ceres, the largest asteroid in the asteroid belt, we'd have to call that a planet. It's a spherical body that goes around the sun. And Charon, which is Pluto's moon, major moon, we'd have to call that a planet too. So Pluto and Charon would be a double planet. And it gets too complicated then. You start adding all this stuff. So it's better to demote Pluto as a planet so that you can keep things a little bit simpler in your perspective of the solar system. Origin for Pluto, it may be a world that formed with the others, but of course its composition is quite different, so this is not very likely. It may be an escape moon of Neptune because its eccentric inclined orbit sometimes crosses Neptune's path, so maybe they came close at one time. But Pluto is responsible for a moon as well, and in fact it has 3 moons, so this is not very likely because if it were near Neptune, Neptune probably would dominate those other 3 moons as well and not allow Pluto to have control of them. So most likely Pluto is a Kuiper belt object, a KBO, just like the other objects that have been discovered recently from the 1990s. So here we have our solar system, the 9 planets of our solar system. I grew up with the mnemonic phrase that helped you remember the names of the 9 planets. We would say, starting with Mercury, my very excellent mother just sent us 9 pizzas. That's how you remember the 9 planets with that phrase. Unfortunately, Pluto has been demoted, and now the 9 planets of our solar system are now 8 planets as of 2006. So our memory device now might be, my very excellent mother just sent us nothing. Nada. Pluto has a major moon, Charon. Here's a picture taken by the Naval Observatory in 1977. Charon is named after the mythical boatmen who ferried the dead across the river Styx in Hades, so it is a helper to the god Pluto, taken by Naval Observatory. So I tell you, if I look at this picture, it'd be hard to recognize that this extra light over here on this side of this picture is actually indeed another body, looking at it closely. But if you were an astronomer who was taking and took these kind of pictures on a regular basis, you would be able to discern that there are indeed 2 bodies there. Let's see what happens when we look at higher resolution of this picture of Pluto. We see, yep, there's Pluto campaigning for itself to become a planet again. And hence that extra light is just its campaign sign. No, that's not it. Let's look at the higher resolution taken by the Hubble Space Telescope recently, and we can see indeed there are 2 objects there. There's Pluto and Charon. The Hubble Space Telescope has discerned between the 2. Charon's rotation and revolution period around Pluto is 6.4 Earth days, so they are tidally fixed actually to each other. And Charon takes 6.4 Earth days to go around Pluto, and hence, since it's tidally fixed, 6.4 Earth days to rotate on its axis. It has a retrograde revolution and tidally fixed. In 2005, the Hubble Space Telescope was devoted for 3 days to take a long exposure of Pluto, which is amazing that all the astronomers will allow this great telescope to be used for 3 days to take a high-resolution photograph of Pluto. But when the result was that CHARON was clearly discerned, and then 2 other objects were seen to be satellites or moons of Pluto. 3 days later, another long exposure was taken, and indeed, those 2 other objects turned out to be satellites of Pluto. So Pluto has 3 moons. Those moons have now been named to be Nix and Hydra. So Pluto has Charon, Nix, and Hydra, which are 2 more attendants to Pluto. We wish to know more about Pluto, and in 2005, the New Horizons spacecraft was launched on a journey to make it to this outermost dwarf planet now. And it should arrive in 2015. So we're looking forward to when it will get there to take some pictures of Pluto. But here's a picture taken in 2006 by the New Horizons spacecraft on its way to Pluto, and this little dot in the middle of this picture is Pluto as seen from the spacecraft on its way there. It's hard to see much to do with that dot, but with a higher resolution picture taken not much later, we can now see that Pluto is clearly visible rotating on its axis. And with the higher resolution, we see Pluto and its 2 new moons, Nix and Hydra, rotating near Pluto with this higher resolution. Just having some fun. Kuiper belt objects, KBOs. 25% of the KBOs, which is in the Kuiper belt just beyond the orbit of Neptune, have the same orbital period as Pluto. And this is probably due to the gravity of Neptune itself. The orbital periods are 1.5 times that of Neptune. And Pluto is about the same size as the largest KBO, so we're discovering almost on a yearly basis more of these objects that are either close to the size of Pluto, or some of them are even larger than Pluto. And hence, this probably contributed to Pluto losing its planetary status in the year 2006. One of those discovered was Xena, which is smaller than Pluto, just a little bit smaller than Pluto. It was discovered in 2003. There is no good picture of Xena, so I've taken the liberty to use my own artistic expression to show what Xena might look like. Here it looks like the Death Star from Star Wars. Had a confirmed discovery in March 2004. Diameter is 2/3 the diameter of Pluto. It extends to much further away from the Sun than Pluto. So it's only seen for a couple of years in its orbit. It might have a moon, but being the Death Star, probably disintegrate that moon very quickly. Just kidding. Here's an actual picture taken by the Hubble Space Telescope of Xena in March of 2004. And we see Xena is just this little streak across this picture. Xena is only visible 2 years out of its 12,000-year orbit. So you can't call it a planet, because if you did, you have to wait, those 12,000 years to see this planet every once in a while. so we just call it a Kuiper Belt object, or possibly a dwarf planet. In 2003, Xena was discovered. At least that was a name given by the people who discovered it. Xena was discovered in 2003, and it was noted that Xena had a moon, which was named Gabrielle, and in 2005. So here's a picture taken by the Keck Observatory of Xena and Gabrielle. The technical name for Xena and Gabrielle when it was first discovered was 2003 UB313, and the key thing was that Xena was larger than Pluto and twice as far from the Sun, at least in its orbit, than Pluto, which made it actually a relatively close orbit in terms of Kuiper Belt objects to the solar system. But the key factor here was that it was actually larger than Pluto, again giving credence to the idea that Pluto should be demoted from planetary status, because otherwise these other objects have to be promoted to planetary status and it would be chaos. Here's an artist's depiction of Xena and the moon Gabrielle. Actually, when Pluto was demoted to to dwarf planet status, Xena and Gabrielle were renamed more technically, and now their names are Eris and the moon Dysnomia as of 2006. So now that object is Eris and the moon is Dysnomia. Here's an animation of showing Eris and Dysnomia moving across this field of view, hence showing that it's a relatively close object, not a star, moving around the Sun. There are other Kuiper Belt objects. There's Santa, and there's the Easter Bunny, and these are all names given to these objects when they first discovered, and they're just showing that there are large, almost Pluto-sized objects in the Kuiper Belt, given funny names. So as of 2006, our new dwarf planets are Pluto and Charon, and as such, then Ceres has gained a new status as a dwarf planet, Ceres being the largest asteroid in the asteroid belt between Mars and Jupiter. And now Eris is a dwarf planet as well, with its moon Dysnomia. So as we look at our new look at the solar system, we have the 8 planets. We have the dwarf planet Ceres in the asteroid belt. We have Pluto, and we have Eris, and maybe more to come. That concludes our lectures on Chapter 8, a look at the moons, Pluto, and Kuiper Belt objects and ring systems of the outer solar system.